Hello everyone, I'm Chufeng Xiao from the City University of Hong Kong. I'm happy to here introduce our work, SketchHairSalon, this sketch-based hair image synthesis. We aim to produce photorealistic hair images from freehand sketches. Recently, the learning techniques improved the quality and efficiency of image-to-image translation. They allow real-time generation of photorealistic images from diverse inputs, for example, sketches and semantic masks. How about apply deep learning techniques to sketch-to-hair image synthesis if we had hair sketches and the pale hair images? In our work, we developed such a system to help even novice users to create diverse hairstyles with different structures and appearance. In previous years, hair modeling has been widely explored in the computer graphics community. Such techniques might be used for hair image synthesis. However, the modeling processing is often too time-consuming to support real-time performance. In addition, such methods only work well for hairstyles with relatively simple structures. Based on the generative models, several recent works are good at image synthesis conditioned on diverse inputs, for example, attributes or masks. However, the two types of conditions, that is, attributes and masks, only provide coarse-grained user control. Considering local controls, we found Sketch is a good choice to depict the local and global structures of a hairstyle. Several sketch-based methods has been proposed to produce human portrait of facial hair images. Unfortunately, since the attempts either had the results not very faithful to the sketch or had a dominant gap between facial hair and scalp hair, they are hard to apply to our target task. Michigan decouples the representation of hair images into structure, shape, and appearance. There's orientation map for structure and a reference image for appearance. They use sketches to edit the orientation maps and then indirectly control hair structures. This way somehow can manipulate hairstyle via sketching, but there is still some limitation in orientation map. We observe that although an orientation map can provide dense local structure, it easily washes away some key global structures in a hairstyle. For example, along a coherent wisp of hair strands and some T-junctions between two or more wisps, which indicate occlusion relationship. They are obvious in the hair image, but not clear in the orientation map. In contrast, Sketch is a better representation since a color sketch can not only represent local and global structures, but also depict the local appearance. Our another observation is that a hair sketch already implicitly defines the global shape of a hairstyle. So predicting hair shapes from sketches can be more efficient than drawing them manually. Also, we found a hair map is more informative to represent a hairstyle than a binary mask, due to its support for soft boundary. With the above key observations, we present SketchHairSalon, a novel generative framework for synthesizing realistic hair images directly from a small set of color strokes. Now, let's go over the details of the methodology, including hairstyle design sketch interface, dataset preparation, hair sketch to matte synthesis, hair sketch to image synthesis, and hair sketch auto-completion. We develop a sketch-based interface for hairstyle design. Here, I first give you some brief introduction of our interface, and then give you more details about each part.
First, you can choose hairbrush and initialize one desired hair color. And then draw several strokes to define a hair mat. You can also switch to non-hair brush to refine the hair mat. Next, click the Image Generation button and obtain the generated hair image. You can modify these two-stage results jointly.
At the sketch to image stage, you can assign or reassign colors to these hair strokes via color brush to specify your desired hair appearance.
We provide a color brush to change the hair color locally or globally.
Also, we incorporate two novel sketch auto-completion methods to help users design unbraided and braided hairstyles more efficiently.
For unbraided hairstyles, click Auto Completion button and get some suggested strokes at the blank area. You can accept, reject, or refine the result upon the suggestion. For braided hairstyles, you need to first draw two strokes to define braided boundaries. After setting the hairstyle parameters, the braided parts can be generated. Similarly, you can accept, reject, or refine it. And absolutely, you can design the braided and unbraided parts jointly. This is the final result.
Okay, next part is dataset preparation for training. One possible solution is to use an auto-tracing method to simulate user strokes as done in a previous work for facial hair images. However, unlike facial hair images, scalp hair images in our scenario have larger hair regions and complex structures. The auto-tracing method doesn't work well in this case. To address this issue, we construct a hair sketch image dataset by manually tracing hair strokes over hair images and carefully retaining coherent wisps and T-junctions. Besides, we use an off-the-shelf method to extract hair mats from the hair images for sketch-to-mat learning. Our dataset contains 4,500 image mat sketch triplets and covers hairstyles with different appearance and structures, like straight, wavy, and braided. To train the sketch-to-mat network, we introduce no hair strokes to reduce the ambiguity of hair shape. The no hair strokes are randomly extracted from each hair contour to roughly indicate hair boundaries. With the dataset, now we can train our two-stage system. The first stage, sketch-to-mat, creates a hair mat given user's sketch input. With the sketch and the hair mat as input, the second stage generates the hair images, blended with the original background. Next, I will introduce each stage in more detail. For sketch-to-mat synthesis, the network takes as input the sketch with hair strokes and no hair strokes and produce a hair mat for the next stage. It has a similar architecture to UNet, a classic CNN network for image-to-image translation. We introduced 3 attention modules to help the network learn long-range dependencies among strokes. For sketch-to-image synthesis, we adopt another network similar to sketch-to-mat 1. The key difference here is its incorporation of a background blending module. The background region is blended with the synthesized hair region on the feature level, guided by the hair mat. We conduct feature blending at the last 4 layers. For braided hairstyles, the network needs to learn a general shape from the braided sketch. However, Using only L1 loss, we made S2I net result to spreading the color texture around the sketch, not forming the clear braid shape. To address this issue, we introduce a shape reconstruction loss for braided hairstyle generation. The shape loss smooths both the result and ground truth by a Gaussian fit, and then computes their L1 loss. We observe that most of hairstyles had simple but larger regions with similar local structures that need to be filled with repetitive hair strokes. To reduce the user's role, we propose two sketch auto-completion methods given sparse strokes for the braided and unbraided hairstyles, respectively. For a braided hairstyle, it typically has many repeating nodes, which follow the braided theory. According to it, we first construct the 5 parametric braided 3D models, including fishtail, rope, 3-strand, 4-strand, and 5-strand. Next, we introduce a simple method for users to control a desired braided hair shape via 2 roughly drawn strokes. Here, we take a 3-strand braid as an example. Users first draw 2 blue strokes, which indicate the position and boundary of a target braided sketch. The middle one in figure A shows 3 intertwining centralized constrained by the 2 strokes. The right one is the user-guided model after expanding the 3 centralized to 3 tubes. We also provide a variable W to control the number of braided nodes and the node direction in the braided models. Figure B shows 3 models under different parameter settings. Then we extract the braid edge at the braided sketch using the Kenny algorithm. The color sketch can be derived by setting edge colors upon the color palette from the 3D model. Condition on the auto-completed sketch, photorealistic braided images can be synthesized by our S2M net and S2I net. The right figure shows the generated images with different appearance by changing the sketch colors. For unbraided hairstyles, our main idea is that the input strokes can be diffused to the rest of the hair region. To achieve this, we first apply a dilation operation and subtract the binary mask. Given the candidate regions, we use a medius axis extraction algorithm to automatically extract strokes. So, what the additional strokes provide? In this example, we assign all the strokes with the same color to find out the effect of the additional strokes. First, they can provide more details in the regions which are not well covered by the user's specified strokes. Besides, we find the sparse input will cause appearance ambiguity for S2I net in large hair regions, while the additional strokes help produce more consistent appearance with the input color. We also compare our results with the auto-tracing based method to show the superiority of our method. Now, let's show our results and evaluation. First, we evaluate the quality of the generated mask. The sketch-to-mat network takes as input the hair strokes and no-hair strokes. Compared to the model without attention modules, our full models produce more plausible results as reflected by the differences between the generated results and the target mat. Here, the deeper blue reflects higher error. In our pilot, we directly feed an input sketch to the generation network to produce a hair image, instead of predicting an orientation map from the sketch as an intermediate input as done in Michigan. Although we have found that the sketches can provide enough information for learning sketch-to-image translation, we are still interested in whether orientation map is necessary for hair image generation. So we use the orientation maps predicted from hair sketches to train 2 more sketch-to-image models. One model tests as input only the orientation maps, while the other one takes as input both orientation maps and hair sketches. As the results show, the model with only an orientation map generates flattening hair textures and blurry boundaries of hair wisps. Also, using the orientation map only does not allow appearance control. Incorporating both orientation map and sketch can alleviate these issues to some extent. However, the orientation maps still limit the hair sketches to display their global structures in the network compared to our results. So we believe that the correct hair sketches are good enough to depict the hair shape, structure, and appearance. We compare our method with the SOTA methods for sketch-based hair image synthesis in terms of visual quality. For hair comparisons, we train all the networks on our training dataset with the same inputs as hair sketch and hair mat. It can be easily seen that our method produces more realistic synthesized results. We conducted 2 types of user studies to evaluate the performance of our system, including a perception study and a usability study. The perception study including 3 parts: natural needs study, sketch faithfulness study, and fidelity study. It was conducted via these 3 aspect questionnaires to get feedback from 36 participants. Each of them was provided groups of the result generated by the compare methods. It is obvious that our method achieved significantly better evaluation than the others. For the usability study, since we are interested in checking whether our system would help users with little training in creating hairstyles, we invited 6 such users to test the usability of our system. The study ended with a questionnaire of the customized 5-point US. All of them believed that our system was efficient and helpful for hairstyle design, with a large diversity in structure and appearance. And this figure shows the user design hairstyles. It can be seen that the generated hair images are faithful to the input sketches with different structure and appearance. Here, I will show a demo video showing the hairstyle design process with our system. It includes 2 examples, one for braided hairstyles and the other for braided hairstyle. While our system is able to achieve impressive results, it has several limitations. First, it is hard to resolve complex layering effects merely from sketches, as the top example shows. Next, some hairstyles themselves are hard to be depicted by sketches, so it is also difficult for the sketch-to-image network to produce them from sketches. Additionally, in some cases, the lighting condition is inconsistent between the hair region and the background, which is an open problem. Since our system is mainly for hairstyle design from scratch, but no hairstyle editing, users can only design new hairstyles completely covering the original hair. In the future, we are interested in extending our approach to hairstyle editing. In summary, this will propose a novel system for non-professional users to create photorealistic hair images from freehand sketches. We construct a 2-stage framework for sketch-to-mat and sketch-to-image generation. Based on it, we develop an intuitive sketch-based interface for hairstyle design with 2 novel hair sketch auto-completion features. In addition, we create a dataset of hair sketch image pairs with corresponding hair maps. Thank you for listening. If you are interested, you can refer to our project page for more details. And if you have any questions, welcome to contact us via this email. Thank you.